A supernova is the sudden, violent explosion of a star at the end of its life. Imagine a massive star living out its life in space, shining bright and steady, like a fire burning through logs. The star uses up its fuel over time, and when it can no longer produce enough energy to support itself, it begins to collapse under its own gravity. This collapse happens very quickly, and it causes the core of the star to heat up and become very dense. As the core becomes more compressed, it triggers a powerful explosion that can outshine an entire galaxy for a short time. Stars are like giant factories that produce energy through nuclear reactions in their cores. These reactions start with hydrogen atoms fusing together to form helium, releasing energy in the process. This energy pushes outward, keeping the star stable against the force of gravity pulling inward. But as a star ages, it eventually runs out of hydrogen in its core. When this happens, the star begins to fuse heavier elements like helium, carbon, and oxygen, which produces less energy. Eventually, the star can no longer support itself, and gravity takes over. When the star collapses, it triggers an immense shockwave. This shockwave is the supernova. The outer layers of the star are blown off into space, while the core may shrink into an incredibly dense object, like a neutron star, or even collapse all the way into a black hole. The explosion releases an enormous amount of energy, enough to create new elements and send them hurtling through space. These elements can later form new stars, planets, and even life. A supernova happens in two main ways. One involves a massive star, much larger than our Sun. These stars go through a series of stages, each one burning a different type of fuel. When they run out of the fuel needed to hold up against gravity, the core collapses, and the outer layers are expelled in a giant explosion. This type of supernova is known as a Type II supernova, or core collapse supernova. The other type of supernova occurs in a binary star system. In this case, one of the stars is a white dwarf, a dense, compact remnant of a smaller star. Over time, the white dwarf may pull matter from its companion star. As the white dwarf accumulates more mass, it becomes unstable. When it reaches a critical mass, it explodes in what is known as a Type Ia supernova. In this case, the explosion is triggered by the white dwarf's sudden collapse. The light from a supernova is so bright that it can outshine an entire galaxy for a short period. This sudden burst of energy travels outward in all directions, and as the shockwave expands, it heats up the surrounding gas and dust, making it glow. The explosion produces a wide range of light, from visible to ultraviolet to X-rays. The bright light is accompanied by the release of neutrinos, which are tiny, nearly massless particles that can pass through almost anything without interacting with it. Despite being invisible, neutrinos are a key part of a supernova, as they carry away much of the energy from the explosion. Supernovae play a crucial role in the life cycle of the universe. They are responsible for creating many of the heavier elements in the periodic table, like gold, iron, and uranium. These elements are scattered across space, where they can later become part of new stars, planets, and even living organisms. Without supernovae, the elements needed for life as we know it would not exist. One of the most famous supernovae observed by astronomers is SN 1987A, which exploded in a nearby galaxy called the Large Magellanic Cloud. This supernova was particularly important because it allowed scientists to study the process of a star's death up close. They could observe the shockwave, the explosion of material, and the formation of a neutron star in the center. SN 1987 provided valuable insights into how stars die and what happens afterward. Supernovae are not just important for creating elements, they also serve as cosmic markers for measuring distances in the universe. Astronomers use the light from Type Ia supernovae, which have a consistent brightness, to determine the distance between galaxies. By studying the way the light from these supernovae dims as it travels through space, scientists can map out the vast distances between objects in the universe. Despite their importance, supernovae are rare events. Most stars, even massive ones, do not go through a supernova explosion. In fact, only about 1 in every 100 stars will end its life in this way. The process is extremely violent and catastrophic, releasing a huge amount of energy in a very short amount of time. However, when they do occur, supernovae leave a lasting mark on the universe, changing the structure of galaxies and the composition of space. When a supernova happens, it is a dramatic event, but it also has a more subtle, long-term impact. The explosion sends shockwaves through the surrounding space, and over time, these shockwaves help to create new stars and galaxies. The elements thrown out by the explosion become part of the gas clouds that form new stars. This means that supernovae not only end the lives of individual stars, but also contribute to the creation of future generations of stars, planets, and even life in the grand scale of the universe. Supernovae are important markers of the end of one era and the beginning of another. They are a reminder of the ongoing cycle of birth, death, and rebirth that governs the cosmos. They are both destructive and creative, causing massive changes in the universe, while also paving the way for the creation of new worlds and stars. The next time you look up at the night sky and see the stars twinkling above, remember that many of those stars have gone through the process of birth and death, much like the stars that create supernovae. Their light is a reflection of the ongoing cycle of the universe, constantly evolving and changing over time. A hypernova is a rare and far more powerful version of a supernova. It happens when a star far more massive than the Sun collapses at the end of its life. While a typical supernova might involve a star several times the mass of our Sun, a hypernova occurs when the star is at least 30 times more massive. This leads to a far more intense explosion, one that can release energy hundreds of times greater than a regular supernova. The aftermath of a hypernova can be catastrophic, but it also plays a role in shaping the universe. To understand a hypernova, it helps to first look at a supernova. A supernova happens when a star runs out of fuel, causing it to collapse under its own gravity. This collapse triggers a massive explosion that sends the outer layers of the star flying into space. In the case of a hypernova, the star involved is much larger. These stars are giant in comparison to our Sun, burning through their fuel much faster and with much more power. The process leading to a hypernova is similar to that of a supernova, but on a much grander scale. A massive star will eventually run out of hydrogen fuel, the primary source of energy for most stars. As it runs out of fuel, the core of the star begins to collapse under gravity, and the outer layers start to expand. However, unlike smaller stars, which may collapse into a neutron star, the core of a massive star will collapse into a black hole. The collapse is so intense that it creates a gravitational pull so strong that not even light can escape it. When this happens, the outer layers of the star are ejected violently into space, creating the explosion we observe as a hypernova. The shockwave from this explosion travels outward, and the energy released can be billions of times brighter than the Sun. It's so intense that it can briefly outshine an entire galaxy. The radiation from the blast is capable of affecting nearby stars and planets, stripping away their atmospheres and potentially sterilizing them. The shockwave also sends out a burst of gamma rays, which are one of the most powerful forms of energy in the universe. These gamma ray bursts, often associated with hypernovae, are brief but extremely energetic, capable of traveling vast distances through space. The energy released in a hypernova is not only enormous but also very important. It plays a major role in the creation of heavy elements. During the explosion, the temperatures and pressures are so extreme that new elements are formed. These elements, which are heavier than iron, are blasted into space, where they can eventually form new stars, planets, and even life. This is how many of the heavy elements on Earth, such as gold and uranium, came to be in the first place. Without hypernovae, these elements wouldn't exist, and the universe as we know it would be very different. Hypernovae also produce what is known as a gamma-ray burst, GRB. These bursts of energy are incredibly powerful and can last from a few seconds to several minutes. They are among the most energetic events in the universe, releasing more energy in a few seconds than our Sunday will in its entire lifetime. These bursts are so bright that they can be detected across billions of light years of space. If a gamma-ray burst were to occur close to Earth, it could have serious consequences. It could strip away the atmosphere, exposing the planet to harmful radiation. Fortunately, gamma-ray bursts are rare, and Earth is located far enough from any potential hypernova that we are not in danger of such an event. Hypernovae are often found in regions of space where massive stars are born. These stars tend to form in areas where there is a lot of gas and dust, such as in star-forming nebulae. The conditions in these regions allow massive stars to form, but it also means that when they reach the end of their lives, the resulting explosions can be far more destructive than in other areas of space. One famous example of a hypernova is the explosion of a star in the constellation of Ursa Major, which was observed by astronomers in 1998. This event, named SN 1998 BW, was one of the most powerful explosions ever recorded. The energy released in this hypernova was equivalent to the total energy output of several billion suns, making it a remarkable event in the study of stellar deaths. The explosion was linked to a gamma-ray burst, which provided scientists with valuable data on how these intense events occur. Hypernovae can also have a significant effect on the space around them. The shock waves from the explosion can trigger the formation of new stars by compressing gas and dust in nearby regions. This process, known as star formation, is one of the ways the universe continues to evolve. The explosion of a hypernova is both destructive and creative, reshaping the surrounding space and contributing to the creation of new stars, planets, and other celestial objects. Because hypernovae involve the collapse of massive stars, they are relatively rare events. Only a small fraction of stars are massive enough to end their lives in a hypernova. Most stars, like our Sunday, are not massive enough to undergo this process. Instead, they will shed their outer layers and become white dwarfs, leaving behind a more stable remnant. The truly massive stars, however, can end their lives in spectacular fashion, creating a hypernova that can outshine entire galaxies for a brief moment in time. The study of hypernovae is still ongoing as astronomers continue to learn more about these powerful explosions. They provide insight into the life cycles of massive stars, the creation of heavy elements, and the impact of such events on the universe. Hypernovae are a key piece in understanding the complex processes that govern the evolution of stars and galaxies. When a star explodes as a hypernova, the energy released is almost beyond imagination. A hypernova is far more powerful than a regular supernova. While a supernova already releases an incredible amount of energy, a hypernova can release up to 100 times more. To picture this, think about our Sun. If you were to take all the energy our Sun will produce over its entire lifetime of about 10 billion years and release it in a single moment, it would still not match the raw power of a hypernova. That is how intense these events are. A hypernova happens when a very massive star reaches the end of its life. These stars are usually much larger than our Sun, often dozens of times more massive. Over time, the star burns through its fuel. When the fuel runs out, gravity causes the core to collapse inward. This collapse happens in a fraction of a second. The outer layers of the star then rebound and explode outward at incredible speeds. The sudden release of energy produces a burst of light, so bright it can outshine entire galaxies for a short period. Imagine being on a planet in a galaxy far away when a hypernova goes off. If that planet was close enough, the intense light and radiation would be so strong that it could destroy an atmosphere and strip a planet bare. Even if you were thousands of light years away, the light from the explosion would still be visible, shining like a beacon in the night sky. Scientists on Earth have observed some of these explosions using powerful telescopes, even when they occur in galaxies billions of light years away. The amount of energy released can also be measured in terms of what it does to space around it. For example, hypernovae often produce gamma ray bursts. Gamma rays are the most energetic form of light. When a hypernova explodes, it can send out focused jets of these gamma rays at near light speed. If one of these jets were to hit Earth, it would be catastrophic, even from thousands of light years away. Luckily, the odds of a jet pointing directly at us are very low. Scientists think hypernovae may play a role in shaping the universe. The explosion spreads heavy elements like iron, gold, and uranium across space. These elements are created inside the star before it explodes. Without hypernovae and supernovae, planets like Earth would not have the materials needed to form solid surfaces, oceans, or even living beings. In a way, every atom of iron in your blood may have come from a star that exploded long before our solar system existed. To understand the energy scale better, think about the most powerful nuclear bomb ever tested on Earth, the Tsar Bomba. It released about 50 megatons of energy. A hypernova releases more energy than billions of these bombs, detonating all at once. Even our entire sun is tiny in comparison. The total energy output of a hypernova can equal what our sun would produce if it kept shining for 10 billion years, all released in a single event, lasting only a few seconds. Astronomers have been able to study these events using space-based telescopes, like the Hubble Space Telescope and the Swift Observatory. These instruments detect different forms of light, including gamma rays, X-rays, and visible light. By studying the light patterns, scientists can piece together what happened during the explosion. For example, they can estimate how fast the material was ejected, how much mass was involved, and how much energy was released. One famous hypernova was linked to a gamma ray burst detected in 1998. At first, astronomers saw only the burst of gamma rays. Later, they noticed a supernova-like event in the same location. This helped confirm that some gamma ray bursts come from hypernovae. These discoveries have helped scientists understand not only how stars die, but also how black holes might form. When the core of a massive star collapses, it can form a black hole at the center. The material falling into the black hole may power the gamma ray jets seen during the explosion. Another way to look at the energy involved is by comparing it to human experience. Imagine the entire population of Earth using every form of energy we have: burning fuel, harnessing the wind, using nuclear power, all at once. Even if humanity used energy at that level for millions of years, it would still not come close to the energy released by one hypernova. This shows how small our activities are compared to the forces at work in the universe. Hypernovae also leave behind remnants that continue to affect their surroundings. The expanding shell of gas and dust can travel at thousands of kilometers per second, colliding with other material in space. These collisions can trigger the formation of new stars. In this way, the death of one star leads to the birth of many others. Galaxies are shaped by this cycle of star death and rebirth, and hypernovae play a key role because of their sheer power. Scientists are still learning about these events. They run computer models to simulate what happens inside a star just before it explodes. These models require huge amounts of data and powerful computers, because the physics involved is so complex. By comparing the models to actual observations, researchers refine their understanding of how hypernovae work. This research helps explain not only the life cycles of stars, but also the history of the universe itself. In the future, new telescopes will allow us to see hypernovae even more clearly. The James Webb Space Telescope, for example, can detect faint light from very distant galaxies. This means it might observe hypernovae that occurred billions of years ago, near the beginning of the universe. These observations will help answer questions about how the first stars formed and how the elements needed for planets and life were spread across space. The idea that a single event can release as much energy as an entire galaxy of stars shows how violent and dynamic the universe can be. Hypernovae remind us that even though space may seem calm when we look up at the night sky, it is filled with powerful forces at work. Each explosion is a brief moment of extreme energy, shaping the universe on a scale far beyond our everyday experience. When a star reaches the end of its life, the size of the star plays a key role in determining how it will die. Supernovae and hypernovae are both the results of a star's death, but the size of the star at the beginning of its life influences how these events unfold. Supernovae typically happen in stars that are between 8 and 20 times the mass of our Sunday. Hypernovae, on the other hand, occur in stars that are much larger, more than 30 times the mass of the Sunday. Stars are born from vast clouds of gas and dust in space. As the material comes together under gravity, it forms a dense core that heats up, eventually starting nuclear fusion. The process that powers a star, the mass of the star, determines how long it will live and how it will end. Smaller stars, like our Sunday, live for billions of years, but larger stars burn through their fuel much faster. A star that is 8 to 20 times the mass of the Sunday will go through its fuel quickly and reach the end of its life in just a few million years. For stars of this size, when the fuel runs out, the core collapses under its own gravity. As the core shrinks, it heats up, causing the outer layers of the star to explode outward in a massive burst of energy. This is what we see as a supernova. The explosion releases an incredible amount of energy, brightening the star for a brief period, sometimes outshining the entire galaxy. The energy from the explosion can be so strong that it forms new elements, like gold and iron, which are scattered across space. These elements later go on to form new stars, planets, and even life. While supernovae happen in stars with masses between 8 and 20 times the mass of the Sunday, hypernovae occur in stars that are much larger, at least 30 times the mass of the Sunday. A star this large goes through a similar process as a smaller star, but the differences in size lead to a far more powerful explosion. The core of a hypernova star collapses just like a supernova star, but because the star is much more massive, the collapse is even more extreme. The gravity at the core is stronger, pulling the star's material in more quickly and more forcefully. The collapse generates far more heat and energy, triggering an explosion that is 100 times more powerful than a supernova. In the case of a hypernova, the energy released is so intense that it can create a black hole at the center of the explosion. This black hole is formed when the core collapses to an incredibly small and dense point. The energy released by the formation of a black hole, combined with the shock wave of the explosion, results in a hypernova, an event so powerful that it can briefly outshine an entire galaxy. The size of the star also affects the way the explosion occurs. In a regular supernova, the outer layers of the star are blown away, and the core may become a neutron star, or in some cases a black hole. But in a hypernova, the force of the collapse and the explosion is so great that the entire core can collapse into a black hole. The result is a burst of energy that is far more intense and lasts for a shorter period compared to a supernova. When we compare the size of the star to the end result, it's clear that the larger the star, the more dramatic its death. A supernova from a star 10 times the mass of the Sunday is already an incredible event. But a hypernova from a star 30 times the mass of the Sunday is orders of magnitude more intense. This difference is due to the size and mass of the star. More massive stars have more fuel to burn and produce more energy, leading to a far more powerful explosion when they die. The energy released by these explosions is not just important for the star itself, but also for the surrounding space. A supernova or hypernova can trigger the formation of new stars by compressing nearby gas and dust clouds. These shock waves can stir up nearby material, creating new regions where stars and planets can form. In this way, the death of massive stars is closely tied to the birth of new stars. A star's size and mass directly influence how it ends, but they also influence what comes next. While the size of the star determines whether it will become a supernova or a hypernova, it's not just about the mass. The conditions inside the star also matter. For instance, the way the star burns its fuel and the amount of time it spends in each stage of its life will affect the explosion's intensity. In both supernovae and hypernovae, the star's core eventually becomes unable to support the outer layers, leading to a collapse. But the size of the star determines how much fuel it has left, how fast it collapses, and what type of remnants are left behind. Stars that are 8 to 20 times the mass of the Sunday go through a series of stages before they die. They burn hydrogen in their cores for most of their lives. But as they run out of fuel, they begin to fuse heavier elements. When they finally run out of fuel to burn, they can no longer support their own weight. The outer layers of the star are blown away in the explosion, and the remaining core may become a neutron star. This is the supernova, a powerful but relatively smaller explosion compared to the death of a much larger star. For stars over 30 times the mass of the Sunday, the process is similar, but the collapse is much more extreme. These stars have far more mass, meaning they have more fuel to burn, and can create far higher pressures and temperatures at their cores. The result is a much stronger gravitational pull, causing the collapse to happen much faster. The end result is not just a massive explosion, but a hypernova, an event that can briefly outshine an entire galaxy and release hundreds of times more energy than a typical supernova. The size of the star is not the only factor that determines whether it will end as a supernova or a hypernova, but it is by far the most important. The larger the star, the more mass it has to burn, and the more energy it will release when it finally dies. Hypernovae, which occur in stars over 30 times the mass of the Sunday, are among the most powerful and dramatic events in the universe. Their explosions are so intense that they can briefly outshine entire galaxies and trigger the formation of new stars and elements. In the end, the size of the star is a defining factor in determining how it will die. Smaller stars, like our Sunday, will shed their outer layers and become white dwarfs or neutron stars. Larger stars, those between 8 and 20 times the mass of the Sunday, will end their lives in supernovae, releasing enormous amounts of energy. But for the biggest stars, those over 30 times the mass of the Sunday, the death of the star is marked by the much more intense and powerful explosion of a hypernova. A hypernova is one of the most powerful events in the universe, releasing an amount of energy that dwarfs the explosion of a typical supernova. While a supernova is already an incredible burst of energy, a hypernova can release up to 100 times more energy. This immense release of energy makes a hypernova one of the brightest and most intense explosions in space. To understand the scale of this energy, think of the energy output of our Sunday. The Sunday, a relatively small star compared to some others in the universe, produces about 3.8 Fe 10 circumflex 26 watts of energy every second. A supernova already releases an enormous amount of energy, typically around 10 circumflex 44 joules, but a hypernova releases as much as 10 circumflex 46 joules. That's 100 times more energy, enough to light up the entire galaxy for a brief period. The process begins when a massive star often much larger than the Sunday, reaches the end of its life. Like all stars, these massive stars burn through fuel in their cores through nuclear fusion. As they burn through their fuel, the star grows unstable. When a star that's at least 30 times the mass of the Sunday runs out of fuel, its core begins to collapse under gravity. In a regular supernova, this collapse creates a neutron star, or sometimes a black hole. But in a hypernova, the collapse is so extreme that it leads to an even greater release of energy. This massive energy comes from both the collapse of the star's core and the violent explosion of its outer layers. As the core compresses under the force of gravity, temperatures soar to incredible levels. The heat and pressure inside the core become so intense that they trigger a powerful explosion, sending out shock waves and releasing vast amounts of energy in the form of light, heat, and radiation. The energy released by a hypernova is many times greater than the energy output of the entire star during its lifetime. One of the main contributors to the energy of a hypernova is the formation of a black hole. When the core of the massive star collapses, it can create a black hole with a gravitational pull so strong that nothing can escape it, not even light. The creation of the black hole is accompanied by a tremendous burst of energy. This energy is released in a variety of forms, including gamma rays, which are some of the most powerful types of radiation in the universe. Gamma ray bursts are one of the most striking results of a hypernova. These bursts of radiation can travel across vast distances and are so intense that they can briefly outshine an entire galaxy. In fact, a gamma ray burst from a hypernova is one of the most energetic events ever observed. These bursts last only a few seconds or minutes, but in that time they release as much energy as our Sunday will in its entire lifetime. If a gamma ray burst were to occur close enough to Earth, it could have catastrophic consequences, potentially stripping away the atmosphere and causing a mass extinction. Fortunately, gamma ray bursts are rare, and Earth is located far enough from any potential hypernova to be safe. Hypernovae also produce heavy elements such as gold, uranium, and platinum, which are created in the extreme conditions of the explosion. The temperatures inside a hypernova are so high that they allow the formation of these heavy elements through a process called nucleosynthesis. These elements are then scattered across space, where they can eventually become part of new stars, planets, and even life itself. Without hypernovae, the universe would lack many of the essential elements that make up planets like Earth. To put this energy into perspective, consider that the energy released by a hypernova is so immense that it can affect the surrounding space. The explosion sends shockwaves through the surrounding gas and dust, heating it to extreme temperatures and causing it to glow brightly. This release of energy can trigger the formation of new stars by compressing gas clouds and triggering nuclear fusion in the new stars. So, while a hypernova is a destructive event, it also plays a role in creating new stars and shaping the future of the universe. The energy released in a hypernova can also cause a massive disruption in its local region of space. For instance, the shock waves from the explosion can travel across light years, affecting nearby stars, planets, and even entire galaxies. In some cases, the shock wave can strip the atmospheres of nearby planets, potentially making them uninhabitable. The explosion can also cause other stars to form or explode, further changing the dynamics of the region. Hypernovae are incredibly rare, and only the most massive stars end their lives in this way. Stars that are smaller than 30 times the mass of the Sunday generally won't have the energy needed to trigger such an intense explosion. Most stars, including our Sunday, will eventually shed their outer layers and become white dwarfs or neutron stars without undergoing a hypernova. But for the stars that are massive enough, the result is an explosion of unimaginable power. The amount of energy released by a hypernova is so vast that it can affect even distant galaxies. The explosion can send shock waves through space, compressing gas and dust clouds in other regions, potentially leading to new star formation, or even the triggering of another hypernova. In this way, hypernovae play a role in shaping the structure and evolution of galaxies. Astronomers study hypernovae to understand the behavior of massive stars and the creation of heavy elements in the universe. By observing the light and radiation released by these events, scientists can gain insight into how stars live and die, as well as the processes that create the elements necessary for life. Hypernovae are a reminder of the raw power and immense forces at work in the universe. They help us understand the balance between creation and destruction as stars end their lives in the most spectacular way possible. In the end, the energy released by a hypernova is a testament to the vast forces of nature that govern the cosmos. These explosions are not only powerful, but also play an essential role in shaping the universe, creating new elements and influencing the formation of new stars. The next time you look up at the stars, remember that some of those distant points of light may have once been part of a massive star that exploded in a hypernova, sending out energy that shaped the universe in ways we are just beginning to understand. A hypernova is far brighter than a supernova, releasing more light and energy than most events in the universe. While supernovae can briefly outshine entire galaxies, hypernovae take brightness to an extreme. These explosions are so intense that they can be seen from billions of light years away, making them visible across vast stretches of space. To understand this brightness, it is helpful to think about the scale of light in the universe. A supernova, which happens when a star between 8 and 20 times the mass of the Sun reaches the end of its life, releases an enormous amount of energy. This explosion can briefly become so bright that it outshines the entire galaxy it resides in. The amount of energy released is equal to the total energy output of the star over its entire life. This kind of brightness is visible across galaxies, but it's just a fraction of the intensity that a hypernova produces. Hypernovae happen in stars that are at least 30 times the mass of the Sun, significantly more massive than those that create regular supernovae. These stars burn their fuel much faster and with much greater force. As the star reaches the end of its life and collapses, it triggers an explosion much more powerful than that of a supernova. The result is an explosion that can be up to 100 times more energetic than a typical supernova. The brightness of a hypernova comes from the sheer amount of energy released in a very short time. The light emitted during the explosion can outshine the star by billions of times. This extreme release of energy can cause the hypernova to shine brighter than an entire galaxy for a brief period. In fact, the explosion is so bright that it can be visible across distances of billions of light years. To put that in perspective, light from Earth's Sun takes only about 8 minutes to reach us, but light from a hypernova can travel billions of light years and still be detected by telescopes on Earth. When a hypernova explodes, it releases a broad range of radiation. While the visible light is what we can see with our eyes, the explosion also emits X-rays and gamma rays, which are forms of radiation far more energetic than light. These bursts of radiation are so powerful that they can affect space far beyond the site of the explosion. For instance, a gamma ray burst from a hypernova can travel across vast distances and potentially disrupt the atmospheres of nearby planets, sterilizing them. Luckily, hypernovae are rare, and Earth is far enough away from any potential sources of these bursts to avoid harm. The brightness of a hypernova is also tied to its duration. While supernovae typically remain visible for a few weeks or months, the light from a hypernova can last longer and reach greater distances. It's not just that a hypernova is bright in the moment of explosion, but the energy released continues to shine through space, allowing it to be seen from further away. This allows astronomers to study hypernovae and their aftermath, even if they occurred billions of years ago. The energy released in a hypernova is not only incredibly bright, but also carries enough force to spread across space, impacting everything in its path. The explosion sends out shockwaves that can affect nearby stars, gas clouds, and planets. The energy and light released can cause nearby objects to heat up and glow, which can trigger the formation of new stars. These shockwaves can also push material away from the explosion, helping to scatter elements like iron, gold, and uranium across space. These elements are then recycled in new stars and planets, continuing the cycle of stellar life and death. One of the most famous examples of an extremely bright explosion is the hypernova associated with gamma ray burst GRB 080916c. This gamma ray burst, which originated from a distant galaxy, was detected as one of the most energetic and brightest explosions ever observed. The explosion was so powerful that it was visible across billions of light years, making it one of the farthest and most intense explosions ever recorded. Scientists were able to study the light and radiation emitted from the hypernova to learn more about the conditions in the star before it exploded, as well as the effects of the explosion on its surroundings. In addition to their extreme brightness, hypernovae play a critical role in the universe's ongoing cycle of creation. The energy released during the explosion creates conditions that allow for the formation of new elements, and even new stars. As the shockwaves from the explosion travel through space, they compress gas and dust clouds, triggering the birth of new stars. The elements created in the explosion are scattered throughout space, enriching the interstellar medium and providing the raw materials for new planets and other celestial bodies. The brightness of a hypernova also helps astronomers study the universe. When a hypernova occurs, it is one of the most noticeable events in the sky. Because of its extreme brightness and the range of radiation it releases, it acts as a cosmic marker. Astronomers can use the light from hypernovae to measure distances in space, helping them map out galaxies and other cosmic structures. The brightness allows them to study the explosion in detail, learning more about the star that caused it and the properties of the surrounding space. Despite their brightness, hypernovae are rare events. Only the most massive stars, those more than 30 times the mass of the Sun, have the energy to produce these extreme explosions. Most stars, including our Sun, won't end their lives in a hypernova. Instead, they will shed their outer layers and become white dwarfs or neutron stars. This makes hypernovae even more significant when they do occur. Their extreme brightness not only signals the death of a massive star, but also provides insights into the life cycle of stars, the formation of elements, and the structure of the universe. The brightness of a hypernova can be overwhelming, but it is also a reminder of the vast scale and power of the universe. These explosions are some of the most energetic events known to science, capable of lighting up space for millions of light years. They not only release a dazzling amount of light, but also help shape the universe, creating new stars and elements in the process. The sheer brightness of a hypernova is a testament to the scale of the forces at work in the cosmos, revealing the immense power that exists in the death of a star. When a star reaches the end of its life, the way it dies depends on its size. For the largest stars, those more than 30 times the mass of the Sun, their deaths often result in the formation of black holes. These stars go through a process that leads to a hypernova, an explosion far more powerful than a typical supernova. The collapse of the star's core in a hypernova is so intense that it creates a black hole, an object with gravity so strong that not even light can escape it. A black hole forms when a massive star's core collapses under its own gravity. For stars with masses over 30 times the Sun's, the collapse is so extreme that it doesn't stop at forming a neutron star, which is what happens in less massive stars. Instead, the core becomes dense enough that it keeps collapsing into an infinitely small point, creating a black hole. The energy released during a hypernova explosion contributes to this process. but it is the collapse of the core itself that forms the black hole. A black hole is a strange and powerful object. It is not an empty space, but rather a region where gravity is so strong that it warps space and time around it. Once a black hole forms, it pulls in everything around it, including light. This is why we cannot see black holes directly. The light gets trapped. However, the effects of a black hole can be seen in other ways. For example, matter that gets too close to a black hole is heated up to extremely high temperatures, causing it to glow brightly. This gives us indirect evidence of a black hole's presence. Not all stars create black holes, though. In stars with masses between 8 and 20 times the mass of the Sun, the outcome is often different. When these stars explode in a supernova, their cores may collapse, but instead of forming a black hole, they form a neutron star. Neutron stars are incredibly dense remnants of a star's core, much smaller than the original star, but still containing a mass greater than that of the Sun. The collapse of the star's core creates a neutron star when the force of gravity is balanced by the pressure of neutrons, which are subatomic particles packed tightly together. The difference in the final outcomes, black hole versus neutron star, depends on the mass of the star. If the core of the collapsing star is heavy enough, the force of gravity will overwhelm all other forces and cause the core to collapse into a black hole. If the core is not massive enough, it will form a neutron star. The boundary between forming a neutron star and a black hole is a fine one, and it depends on how much mass remains after the supernova explosion. The process of black hole formation is a crucial part of how the universe evolves. When a black hole forms, it not only marks the end of a massive star's life, but also plays a role in shaping the galaxy around it. Black holes can grow larger by pulling in gas, dust, and even other stars. This process is how supermassive black holes at the centers of galaxies form. These black holes can become billions of times the mass of the Sun and influence the structure and dynamics of their galaxies. Hypernovae, and the black holes they create, are also responsible for some of the most energetic events observed in the universe. When a black hole forms after a hypernova, it can send out powerful jets of energy. These jets are made up of particles that move at nearly the speed of light and can stretch across vast distances. These jets are sometimes detected by astronomers as they interact with the surrounding space. The power behind these jets comes from the energy created when the black hole pulls in matter from its surroundings. A well-known example of a black hole formed by a hypernova is the collapse of a star that triggered a gamma ray burst, GRB. Gamma ray bursts are some of the brightest and most energetic explosions in the universe, often linked to the formation of black holes. These bursts are created when a massive star collapses, and the material around it gets pulled into the black hole. The energy released during this process can be so powerful that it is visible from billions of light years away, while hypernovae almost always result in black hole formation. Supernovae are less predictable. For stars with masses between 8 and 20 times that of the Sun, the outcome of the core collapse can be more varied. A supernova might create a neutron star, but if the star is massive enough, it can collapse into a black hole instead. The distinction between a neutron star and a black hole depends on the amount of mass left after the explosion. If the remaining mass is great enough, the core collapses into a black hole. If it's less, it becomes a neutron star. The creation of a black hole from a supernova or hypernova has profound effects on the surrounding space. A black hole's intense gravity can warp space-time, which can cause stars, planets, and even light to follow curved paths around it. This warping of space and time is what leads to the phenomenon of gravitational lensing, where light from distant stars and galaxies is bent as it passes near a black hole. This allows astronomers to detect black holes indirectly by observing the way they affect the motion of nearby objects. Black holes also play a role in the larger structure of galaxies. Many galaxies, including our own Milky Way, have supermassive black holes at their centers. These black holes can influence the movement of stars and gas within the galaxy. In some cases, the energy released by the black hole's accretion disk, made up of gas and dust spiraling into the black hole, can heat up the surrounding material, causing powerful radiation to be emitted. This radiation can affect the formation of new stars and even the overall behavior of the galaxy. While black holes formed by hypernovae are often located far from Earth, they still have an impact on our understanding of the universe. They are one of the most extreme examples of the forces at work in the cosmos. The collapse of a massive star into a black hole not only marks the end of that star's life, but also introduces new dynamics into the universe. Black holes affect the structure of galaxies, influence star formation, and are key to understanding the most energetic phenomena in space. In the end, the creation of black holes is one of the most fascinating outcomes of a star's death. Hypernovae lead almost directly to the formation of black holes, while supernovae may result in either black holes or neutron stars, depending on the mass of the collapsing core. Whether a black hole forms from a hypernova or a supernova, the result is always a profound and far-reaching effect on the universe. The immense gravity of black holes, their ability to pull in matter, and their influence on the surrounding space make them some of the most intriguing and mysterious objects in the cosmos. Gamma ray bursts are the most powerful flashes of energy we know of in the universe. They come from some of the most extreme events in space. When a hypernova takes place, the core of a very massive star collapses. As this happens, jets of material shoot out at nearly the speed of light. These jets produce gamma rays, which are the highest energy form of light. Gamma ray bursts, or GRBs, are the result of this violent process. They are so intense that for a few seconds or minutes they can outshine entire galaxies. A supernova can also create a gamma ray burst, but this is less common. Hypernovae are much more likely to produce them because the stars involved are far more massive and have the right conditions to form these powerful jets. The difference comes from what happens at the core. In a regular supernova, the core may collapse into a neutron star, which is incredibly dense but stable. In a hypernova, the core often collapses into a black hole. As the surrounding material falls toward this black hole, it forms a disk. Magnetic fields and rotation cause some of this material to be funneled into narrow beams. These beams pierce through the star and escape into space as gamma ray bursts. To imagine the scale of this, picture a lighthouse. The light from the lighthouse sweeps across the ocean in a focused beam. Now imagine that instead of ordinary light, this beam carries more energy than all the stars in a galaxy combined. And instead of sweeping slowly, it travels across space at almost the speed of light. If Earth happened to be in the path of one of these cosmic beams, the burst would be incredibly destructive. Fortunately, these bursts are very directional, and the chance of one hitting Earth is low. When scientists first detected gamma ray bursts in the 1960s, they were a mystery. Early satellites, designed to monitor nuclear explosions on Earth, picked up sudden flashes of gamma rays coming from space. For decades, researchers did not know what caused them. It was only in the late 1990s that evidence connected many of these bursts to the deaths of massive stars. This connection became clear when telescopes captured a gamma ray burst followed by the visible light of a hypernova explosion in the same spot. Gamma ray bursts are classified into two main types: short bursts and long bursts. Short bursts last less than 2 seconds and may come from events like the collision of neutron stars. Long bursts last more than 2 seconds and are often linked to hypernovae. These long bursts can continue for several minutes, pouring out vast amounts of energy. When a hypernova creates a long gamma ray burst, The initial flash is usually followed by a glow in other wavelengths of light, such as X-rays, visible light, and radio waves. Scientists call this the afterglow. By studying the afterglow, they can learn about the environment around the explosion and the material ejected by it. One well-known event happened in 1998. Astronomers observed a powerful gamma ray burst, and a few days later, noticed a brightening in the same region of the sky. This was the visible light of a hypernova. It confirmed that at least some gamma ray bursts come from hypernovae. Since then, many other events have been linked in the same way, strengthening this understanding. The energy involved in a gamma ray burst is staggering. In just a few seconds, it can release as much energy as our Sun will produce over its entire 10 billion year lifetime. To compare, the most powerful nuclear bomb ever detonated on Earth, the Tsar Bomba, released about 50 megatons of energy. A gamma ray burst releases energy billions of times greater, all concentrated into a narrow beam. If such a burst happened close to Earth and was aimed directly at us, it could damage our atmosphere and harm life on the planet. Scientists believe that gamma ray bursts might have caused mass extinctions in Earth's distant past. These bursts also play a role in spreading elements throughout the universe. The explosion of the hypernova blasts heavy elements like iron, gold, and uranium into space. The gamma ray burst itself may also affect nearby gas and dust, shaping how future stars and planets form. In this way, hypernovae and their bursts are part of the cycle that creates and destroys matter across galaxies. Detecting gamma ray bursts is challenging because they happen without warning and last for such a short time. Space-based telescopes, like NASA's SWIFT and Fermi satellites, are designed to spot them quickly. When a burst is detected, these satellites alert ground-based telescopes, which then focus on the location to capture the afterglow. This rapid response allows scientists to study the event in detail. The data gathered helps them understand the physics behind these powerful explosions and the life cycles of massive stars. Imagine watching the sky and seeing a sudden flash of light brighter than anything else, lasting only a few seconds. That is how a gamma ray burst would appear if we could see gamma rays with our eyes. After the burst, the afterglow might fade over hours or days. In deep space, these events happen constantly, but they are so far away that only sensitive instruments can detect them. Hypernovae that produce gamma ray bursts are rare, but because the bursts are so bright, we can see them from billions of light years away. This means we are observing events that happened long ago, giving us a view into the early universe. Some of the most distant gamma ray bursts ever detected occurred when the universe was less than 1 billion years old. By studying these ancient bursts, scientists gain insight into how the first stars lived and died. The focused nature of a gamma ray burst is important. Unlike a supernova, which releases energy in all directions, a gamma ray burst channels its energy into narrow beams. This makes it appear even brighter to us if we are in the path of the beam. It also means that many more hypernovae may occur than we detect, because the beams are not always aimed at Earth. For every burst we see, there could be dozens more happening elsewhere, their energy directed into other parts of space. In some cases, a hypernova may produce a supernova, like explosion without a gamma ray burst. This depends on the conditions inside the star before it collapses. If the star has too much material around it, the jets may not break through to space, and no burst is seen. This explains why not every supernova or hypernova is linked to a gamma ray burst. The presence of a burst signals a very specific and extreme set of circumstances. Over time, our understanding of gamma ray bursts has grown, but many questions remain. Scientists continue to study these events using both observations and computer models. Each new detection provides clues about the complex processes involved. Hypernovae and their gamma ray bursts show how violent and dynamic the universe can be. These events release energy on a scale far beyond anything we experience on Earth, and shape the cosmos in ways we are only beginning to understand. When a hypernova occurs, it often leads to the release of a gamma ray burst, one of the most intense explosions in the universe. These bursts are powerful enough to travel vast distances across space, carrying with them a devastating amount of energy. If a gamma ray burst were to occur near a planet, the effects could be catastrophic. The burst could strip away a planet's atmosphere and expose its surface to harmful radiation, potentially making it impossible for life to survive. Gamma ray bursts are the result of a massive star collapsing at the end of its life. In a hypernova, the collapse is especially violent, and the energy released is channeled into focused beams of gamma radiation. These beams are emitted along the poles of the newly formed black hole at the center of the explosion. The energy from these bursts is so strong that it can affect everything in its path, including any nearby planets. The reach of a gamma ray burst is staggering. The burst can travel across thousands, even millions of light years without losing much energy, while the radiation from these bursts is spread over such vast distances that it becomes less intense by the time it reaches distant planets. It is still strong enough to cause damage to anything in its path. The radiation emitted by a gamma ray burst is composed of high-energy gamma rays that can penetrate deep into matter, disrupting atomic structures and potentially causing long-lasting harm to living organisms. One of the most immediate and devastating effects of a gamma ray burst on a planet would be the stripping away of its atmosphere. The intense gamma radiation from the burst would heat the upper layers of the atmosphere to extreme temperatures. This would cause the atmosphere to expand and escape into space, much like the air from a balloon being popped. Once the atmosphere is gone, the planet would be exposed to harsh space conditions, including intense ultraviolet radiation from nearby stars and cosmic rays. Without an atmosphere to protect it, the planet's surface would become inhospitable to life, with any existing life forms being exposed to lethal levels of radiation. Even if the gamma ray burst were to occur at a distance, its effects could still be severe. Planets located within a radius of several thousand light years from the explosion would likely experience significant damage. While the radiation may not be strong enough to strip away the entire atmosphere in every case, it could still cause widespread harm. For instance, the radiation could damage the ozone layer of a planet, allowing harmful ultraviolet light from its star to reach the surface. Over time, this could lead to a collapse of ecosystems, particularly those that rely on protection from the sun's harmful rays. The effects of a gamma ray burst on life would be especially devastating. On Earth, for example, life is protected from much of the sun's harmful radiation by the planet's atmosphere and magnetic field. But if a gamma ray burst were to occur nearby, the radiation would penetrate through the atmosphere and cause widespread damage. Living organisms would be exposed to ionizing radiation, which can break apart molecules in cells, leading to mutations, cell death, and even mass extinction. The destruction of the ozone layer would further increase the exposure of life on the surface to harmful radiation, potentially sterilizing large areas of the planet. There are also indirect effects that could arise from a gamma ray burst. For example, the shock wave from the explosion would send high-energy particles traveling through space, impacting everything in their path. These particles could interact with planets, moons, and even asteroids, potentially changing their orbits or causing them to collide with other objects. The energy from the burst could also affect the interstellar medium, causing clouds of gas and dust to heat up and compress, which could lead to new star formation or trigger other cosmic events. While gamma ray bursts are incredibly rare, their potential to cause widespread devastation means they are taken seriously by astronomers. The likelihood of a gamma ray burst occurring close enough to Earth to to have such an effect is small, but the possibility still exists. There are regions in the universe where hypernovae are more likely to happen, particularly in areas where massive stars are born, such as star-forming nebulae. If a gamma-ray burst were to occur in one of these regions and happen to be directed toward Earth, the effects could be catastrophic. A famous example of a gamma-ray burst that scientists observed was GRB 090423, which occurred about 13 billion light years away. While this burst didn't directly affect Earth, it provides important clues about the potential dangers of these cosmic events. GRBs like this one allow astronomers to study the power of gamma-ray bursts and how they travel across space. By observing these bursts from a safe distance, scientists can learn more about how such events impact their surroundings and what kind of damage they can cause if they occur closer to home. If a gamma-ray burst were to occur within a few thousand light years of Earth, the results could be devastating for life on the planet. The burst could strip away the atmosphere, destroy the ozone layer, and expose life on the surface to lethal levels of radiation. While the chances of such an event happening are low, the potential consequences of even a distant gamma-ray burst make them an important subject of study for astronomers. By understanding the reach and power of these bursts, scientists can better prepare for the unlikely event that one might occur in our galactic neighborhood. The devastation caused by a gamma-ray burst is not limited to the destruction of life. The effects on a planet's environment, such as the loss of its atmosphere and the disruption of its ecosystems, could have long-lasting impacts on the development of life and the habitability of the planet. Even if life were to survive, the changes caused by a nearby gamma-ray burst could be so severe that it would take millions of years for the planet to recover. In this sense, gamma-ray bursts are not just a threat to life, but also to the long-term stability of a planet's environment. When a star explodes in a supernova, it leaves behind a nebula, which is a cloud of gas and dust. This nebula is made up of the material that once formed the outer layers of the star. The explosion disperses these materials across space, creating a colorful and often intricate cloud. This nebula is one of the most visible remnants of the star's death, and it provides a glimpse into the processes that occurred during a supernova. However, when a more massive star undergoes a hypernova, the remnants are much larger and more energetic, often taking the form of a powerful pulsar wind nebula. A supernova remnant begins as the star's outer layers are ejected during the explosion. These layers consist of gas and dust that were once part of the star's outer shells. After the explosion, these materials spread outward into space, forming a nebula. As the gas and dust move outward, they cool and interact with the surrounding environment. The shockwave from the explosion also compresses the gas and dust, triggering new reactions and sometimes even forming new stars in the process. The size and energy of the nebula depend on the size of the star that exploded. In a typical supernova, where a star about 8 to 20 times the mass of the Sun reaches the end of its life, the explosion is powerful, but the resulting nebula is relatively modest in size and energy. The remnants of the explosion continue to expand over time, and the gas and dust slowly dissipate into the interstellar medium. These nebulae can take on a variety of shapes and structures, with some being smooth and spherical, while others are more irregular, shaped by the forces and materials around them. However, when a more massive star explodes in a hypernova, the situation is quite different. Hypernovae occur in stars that are at least 30 times the mass of the Sun. These stars burn through their fuel much faster than smaller stars, and when they collapse, the resulting explosion is much more energetic. The shockwaves from a hypernova are stronger, and the gas and dust left behind are much more energetic. This means that the nebula left behind by a hypernova is larger, denser, and more powerful than the remnant of a typical supernova. One of the key differences between the remnant of a supernova and a hypernova is the presence of a pulsar wind nebula. After a hypernova, the core of the star may collapse into a black hole, but in some cases, it forms a neutron star instead. This neutron star, if it is rotating rapidly, generates a powerful wind of charged particles. This wind, known as a pulsar wind, interacts with the surrounding nebula, creating a bright and energetic structure. The pulsar wind nebula is a highly dynamic and energetic environment where particles move at speeds close to the speed of light, creating intense radiation in the form of X-rays and gamma rays. A famous example of a pulsar wind nebula is the Crab Nebula, which is the remnant of a supernova explosion observed in 1054. The Crab Nebula is powered by a rapidly rotating neutron star at its center, which is emitting a pulsar wind. Although the Crab Nebula is the result of a supernova, not a hypernova, it illustrates how the pulsar wind can create a bright and energetic nebula. In the case of a hypernova, the nebula created by the pulsar wind is even more powerful, often emitting higher energy radiation and extending over a larger area. The energy in a hypernova remnant is not just from the pulsar wind, though the shockwave from the explosion also plays a significant role in shaping the nebula. As the shockwave from the hypernova interacts with the surrounding gas, it compresses the material, heating it up and creating a brighter, more energetic remnant. In some cases, the shockwave can create a bubble of hot gas at the center of the nebula, while cooler, denser material is pushed outward, creating the structure of the nebula. This combination of the pulsar wind and shockwave creates a highly energetic and expanding nebula that continues to shine for millions of years after the hypernova explosion. The size of a hypernova remnant can be much larger than that of a typical supernova remnant. While the nebula from a supernova may stretch across a few hundred light years, the nebula from a hypernova can span thousands of light years. The energy released by the explosion is so great that it continues to affect the surrounding space long after the event. The material in the nebula is often mixed with other gas and dust in the interstellar medium, which can lead to the formation of new stars and planetary systems. The powerful pulsar wind at the heart of a hypernova remnant also contributes to the growth and expansion of the nebula. The wind generates a magnetic field, which in turn accelerates charged particles, creating a bright source of radiation. The energy from the pulsar wind interacts with the surrounding material, producing X-rays, gamma rays, and other forms of radiation that can be detected by telescopes. These high-energy emissions make hypernova remnants some of the most energetic and fascinating objects in the universe. As the nebula expands, it eventually merges with the interstellar medium, and the energy from the hypernova remnant dissipates over time. However, the effects of the explosion linger for millions of years, influencing the environment in which it occurred. The shock waves from the hypernova can trigger the formation of new stars by compressing nearby gas clouds, leading to a cycle of stellar birth and death. In this way, hypernovae not only mark the end of a star's life, but also play a role in the creation of new stars and planets. In conclusion, the remnants of a supernova and a hypernova differ significantly due to the differences in the size and energy of the stars that cause them. While a supernova remnant consists of a relatively modest nebula of gas and dust, a hypernova remnant is far more energetic, often leading to the creation of a pulsar wind nebula. These remnants are larger, brighter, and more powerful, and their effects can be felt across vast distances. The material left behind by a hypernova plays an important role in the ongoing evolution of the universe, influencing the formation of new stars and planetary systems. The energy released by a hypernova continues to shape the surrounding space for millions of years, making hypernova remnants some of the most fascinating and dynamic objects in the cosmos. When a hypernova occurs, it releases an immense amount of energy into the surrounding space. The shock waves produced by the explosion are incredibly powerful and can reach out to nearby stars, gas clouds, and other cosmic objects. These shock waves are not only destructive, they can also have a significant impact on the surrounding environment. One of the most important effects is that they can disrupt the interstellar medium, the gas and dust that fill the space between stars, and trigger new star formation in the process. A hypernova is much more energetic than a regular supernova. This difference comes from the size and mass of the star involved. When a star with a mass of at least 30 times that of the Sunday explodes, it sends out shock waves that are far more powerful than those from a smaller star. These shock waves can travel across light years of space, pushing and compressing the gas and dust in their path. The interstellar medium is made up mostly of hydrogen, the most abundant element in the universe. This material is often spread out and diffuse, but it still has enough density that a shock wave can affect it. When the shock wave from a hypernova passes through the interstellar medium, it can compress parts of it. This compression increases the pressure and density of the gas, which is one of the key factors that can trigger the formation of new stars. The process of star formation begins when a cloud of gas and dust becomes dense enough that gravity starts to pull it together. As the gas and dust collapse, the material heats up, eventually reaching temperatures and pressures that are high enough for nuclear fusion to begin, and a new star is born. The shock waves from a hypernova can serve as a catalyst for this process. When the shock wave pushes through the gas, it forces some parts of it to condense, creating the conditions needed for new stars to form. This effect is not limited to just one star. The shock waves from a hypernova can create a ripple effect, compressing gas clouds in different regions and leading to the formation of multiple stars over time. These newly formed stars could be part of a new generation, and the elements produced in the hypernova explosion can become part of the material that makes up these new stars and planets. The impact of a hypernova's shock waves can also affect existing stars in the vicinity. The explosion can change the orbits of nearby stars, causing them to move differently through space. In some cases, the shock waves can disrupt the balance of a star system, leading to collisions or other interactions between stars and planets. While this type of event is rare, the immense energy released by a hypernova makes it capable of causing significant changes to the surrounding stars and their systems. In addition to triggering star formation, the shock waves from a hypernova can also cause other disruptions in space. The explosion can send particles traveling through space at extremely high speeds, affecting nearby gas clouds, planetary systems, and even entire galaxies. These particles, which are often made of highly energized matter, can interact with other objects in space, influencing their motion or even causing some to be ejected from their orbits. The shock waves can also push dust and gas into new regions, creating dense pockets of material. These regions could become sites for new stars to form. Over millions of years, the effects of the hypernova shockwave could be seen as an ongoing process of star birth and destruction, contributing to the overall evolution of the galaxy. The energy from the hypernova explosion can also disrupt the magnetic fields in the surrounding space. This is important because magnetic fields play a significant role in star formation and the behavior of gas clouds. A change in the magnetic field can alter the way gas clouds collapse, possibly affecting how stars form in the future. The shock waves can also cause turbulence in the surrounding gas, leading to further compression and triggering the formation of stars. This makes the hypernova's shockwave an important driver in the dynamics of star formation. While the shockwaves from a hypernova can trigger the birth of new stars, they can also have destructive effects. The shockwaves and the radiation from the explosion can strip away the atmospheres of nearby planets. If the shockwave hits a planet that is within a certain range, it could expose the surface to harmful radiation, making it inhospitable for life. In the most extreme cases, A hypernova's shockwaves could even cause nearby planets to lose their entire atmosphere, leaving them vulnerable to the harsh conditions of space. The intense energy from a hypernova can also ionize nearby gas, meaning it strips electrons away from atoms. This can change the chemical composition of the interstellar medium, which could have long-lasting effects on the development of stars and planets. The shockwave from a hypernova acts as a powerful force, altering the material it passes through and changing the conditions for future generations of stars and planets. Zone of the more subtle effects of the shockwaves from a hypernova is their potential to accelerate particles to incredibly high speeds. These high-energy particles can travel through space and interact with other matter, affecting the cosmic environment in ways that we are just beginning to understand. These particles can also contribute to cosmic rays, which are high-energy particles that can influence the evolution of life on planets. If a gamma ray burst from a hypernova were to happen near Earth, the cosmic rays could increase the radiation exposure on the planet, potentially affecting the atmosphere and surface conditions. The effects of a hypernova's shockwaves on the surrounding space are part of a larger cycle of stellar birth and death. When stars explode, they not only end their own lives, but also influence the space around them, shaping the future of galaxies and star systems. The shockwaves from hypernovae are some of the most powerful forces in the universe, and their impact can reach across vast distances, affecting gas clouds, stars, planets, and even entire galaxies by pushing gas clouds together, triggering new star formation, and influencing the motion of nearby objects. Hypernovae contribute to the ongoing evolution of the universe in ways that we are just beginning to understand. The power of these shockwaves is immense, and they play an important role in the creation of new stars and the destruction of old ones. The long-term impact of a hypernova's shockwaves can change the structure of galaxies, influence star formation, and even affect the conditions for life on nearby planets. In the grand scale of cosmic events, hypernovae are a force of change, shaping the future of the universe with their powerful shockwaves. When a hypernova occurs, its impact on nearby planets is catastrophic. The intense explosion, along with the radiation and shock waves released, would obliterate any planets in the immediate vicinity. A hypernova is the death of a star at least 30 times the mass of the Sunday, and the amount of energy released during the explosion is so vast that it leaves little chance for any planet close enough to survive. The shockwave, which spreads out from the explosion, is powerful enough to strip away the atmosphere of any nearby planet, rendering it uninhabitable and possibly even breaking apart the planet itself. This level of destruction is a result of the extreme force and radiation emitted by the hypernova, making the survival of planets close to the event highly unlikely. The shock waves from a hypernova travel outward, at speeds approaching the speed of light, carrying immense amounts of energy with them. When these shock waves collide with nearby planets, they would likely cause violent disruptions. The outer layers of a planet could be stripped away, leaving only a barren, lifeless core. If a planet is within a few light years of the hypernova, its atmosphere would likely be completely lost, and the surface would be exposed to harmful radiation, making it impossible for life to exist. The radiation emitted in the form of gamma rays, X-rays, and other high-energy particles could potentially sterilize the surface of the planet, destroying any life forms or conditions that might support life. In the immediate vicinity, the destruction would be so extreme that even the planet itself might be shattered by the shockwave. However, the farther a planet is from the hypernova, the less extreme the effects become. While planets directly affected by the hypernova would face obliteration, planets farther away might still be impacted. But to a lesser degree, the shock waves and radiation would weaken as they travel across space, and while the effects would still be noticeable, they may not be as devastating. Planets within a range of several thousand light years could experience damage to their atmospheres or even have their surface temperatures altered, but they may avoid complete destruction. The atmosphere could be stripped, or the radiation could increase to levels harmful to life, but it would depend on the distance from the event. For example, if a hypernova were to occur within a few hundred light-years of Earth, the radiation and shock waves might still affect our planet. The ozone layer could be damaged, allowing harmful ultraviolet rays from the sunday to reach the surface, potentially disrupting ecosystems and increasing the risk of cancer in living organisms. The increase in radiation could also affect the Earth's climate, making it more difficult for certain life forms to survive. However, such an event would not likely obliterate Earth entirely. The distance between Earth and the hypernova would reduce the energy of the shockwave and radiation, limiting the damage to the planet. Supernovae, which are similar but less extreme than hypernovae, also have the potential to destroy nearby planets, but their effects are much less severe at longer distances. A supernova occurs when a star, typically between 8 and 20 times the mass of the sunday, reaches the end of its life. When the star explodes, it releases a burst of energy that can outshine an entire galaxy for a short time. The explosion sends shockwaves and radiation through space, but the energy released is not as intense as that of a hypernova. As a result, the destruction of nearby planets is less extreme. For planets that are closer to a supernova, the effects would still be severe, but not as overwhelming as in a hypernova. The shock waves could strip away the atmosphere of a nearby planet, exposing the surface to harsh radiation. If the supernova were within a few light-years of a planet, it might be completely destroyed or rendered incapable of supporting life. However, planets farther away would experience much weaker effects. The radiation would diminish over distance, and the shock waves would lose their power. Planets in the outer reaches of the explosion's range could suffer atmospheric damage, but they would likely survive. The likelihood of a nearby planet surviving a supernova is higher than the survival chances of a planet near a hypernova. For planets located farther away from the supernova, the effects are less extreme. Planets several thousand light-years away might experience a slight increase in radiation levels, but they would likely remain intact. This is because the energy of a supernova, though vast, is not as concentrated as the energy from a hypernova. The shock wave from a supernova also dissipates more quickly, reducing the overall impact on distant planets. In comparison, hypernovae are far more likely to cause complete destruction within a larger radius. The immense energy released by the hypernova means that planets located even several thousand light-years away could still be affected. The radiation and shock waves can disrupt nearby star systems, potentially altering their orbits, or even causing them to collide. For planets close to the explosion, survival would be almost impossible. The damage to the atmosphere, the surface, and even the structure of the planet itself would be severe, leaving little chance for life to persist. In both cases, the survival of planets depends largely on their distance from the explosion. The farther a planet is from a supernova or hypernova, the less likely it is to be complete. However, even at great distances, these explosions can still cause significant changes to the surrounding space. They can trigger the formation of new stars by compressing nearby gas clouds, influence the movement of nearby stars, and cause other cosmic events that alter the local environment. Ultimately, the likelihood of survival for planets near a hypernova or supernova depends on the scale of the explosion and the distance from the event. Planets in close proximity to either type of explosion would face severe destruction, with hypernovae being far more likely to result in complete obliteration. As the distance from the explosion increases, the severity of the impact decreases, but even planets that are farther away may still experience some effects. Supernovae, being less energetic than hypernovae, allow for a greater likelihood of survival at longer distances, but planets close enough to the explosion would still be severely impacted. The universe is a dynamic and ever-changing place, where stellar death plays a crucial role in shaping the space around it. Hypernovae are among the most powerful and destructive events in the universe, and the radiation they emit can be life-altering, even at vast distances. The explosion of a hypernova releases a staggering amount of energy, including deadly levels of X-rays and gamma rays. These forms of radiation are far more intense than the radiation from a supernova, and they are strong enough to be lethal to any life forms within a significant radius. If a hypernova were to occur near a planet, the radiation could have catastrophic effects on any living organisms, even at distances far greater than what a supernova would cause. A hypernova is the result of the collapse of a star with at least 30 times the mass of our Sun. During the explosion, the core of the star collapses to form a black hole, and the outer layers of the star are ejected into space. As the material is blasted outward, a massive amount of energy is released, much of it in the form of high-energy radiation, including gamma rays and X-rays. Gamma rays are the most energetic form of light, far more powerful than the visible light we can see. X-rays are also highly energetic and can penetrate through most forms of matter, including living tissue. This intense radiation can travel across vast distances, and its effects would be felt on any planet in its path. The radiation from a hypernova can strip away the atmosphere of nearby planets, removing the protective shield that prevents harmful radiation from reaching the surface. If a planet is close enough, the radiation would likely be strong enough to completely destroy the atmosphere. Without an atmosphere, the planet would be exposed to the full force of cosmic radiation, including ultraviolet rays from nearby stars, cosmic rays, and the deadly gamma rays and X-rays from the hypernova. This exposure would make the planet inhospitable to life as we know it, even if a planet is not in the immediate vicinity of the hypernova. The radiation can still be extremely dangerous. The radiation from a hypernova can travel across light, years of space, and still have a significant effect on distant planets. The farther the planet is from the explosion, the less intense the radiation becomes, but it would still be enough to cause serious damage. The radiation could alter the chemistry of the planet's atmosphere, damage the ozone layer, or even trigger genetic mutations in any life forms that remain. In the worst-case scenario, the planet could become sterilized, with no chance for life to continue or evolve. The intensity of the radiation from a hypernova is one of the key differences between these events and supernovae. While a supernova also releases a huge amount of energy and radiation, the level of intensity is not as extreme as in a hypernova. Supernovae occur when a star between 8 and 20 times the mass of the Sun explodes. The radiation from a supernova is deadly to nearby planets, but the effects are less severe compared to a hypernova. The gamma rays and X-rays from a supernova are powerful, but the energy released is not as concentrated as in a hypernova. This means that while supernovae can strip away atmospheres and harm life, the impact is less intense at longer distances. The radiation from a hypernova, on the other hand, is much more concentrated. This is because the explosion is far more energetic, and the shock waves from the explosion release far more high-energy radiation. The gamma rays and X-rays from a hypernova would be intense enough to cause immediate and lasting damage to any planets within a few thousand light years of the event. A hypernova's radiation could cause widespread mutations, destroy the ozone layer, and even sterilize the planet, making it impossible for life to survive. The radiation from a hypernova could also have a profound effect on the larger environment around it. As the radiation travels through space, it could affect the interstellar medium, the gas and dust that fills the space between stars. This material is often diffuse, but it can be compressed by the shock waves from the hypernova, causing it to become denser. This compression could trigger new star formation, as the gas and dust collapse under their own gravity. The radiation could also change the chemical makeup of the interstellar medium, potentially altering the kinds of elements that are present in the region. This would have long-term effects on the formation of stars and planets in the area. The scale of radiation emitted by a hypernova is mind-boggling. To give some perspective, consider how gamma rays and X-rays from the Sunday affect Earth. The Sunday emits radiation, but Earth's atmosphere and magnetic field protect us from the harmful effects of this radiation. If Earth were directly exposed to the level of gamma rays and X-rays from a hypernova, the results would be catastrophic. The planet's atmosphere could be stripped away, and the surface would be bombarded with lethal radiation. Even if Earth were not directly in the path of the gamma ray burst, the damage to the ozone layer and the increase in radiation could be enough to cause long-term environmental damage, including changes to the climate, a rise in cancer rates, and a collapse of ecosystems. One of the most frightening aspects of hypernova radiation is that its effects can last long after the initial explosion. The radiation from the event would continue to travel through space for millions of years, and even distant planets could continue to feel the effects. The damage to a planet's atmosphere or surface could be long-lasting, with the radiation potentially causing a permanent alteration to the environment. For a planet that is already home to life, this could mean the end of any habitable conditions. The radiation could kill off entire ecosystems and make it difficult, if not impossible, for life to recover. The sheer scale of the radiation emitted by a hypernova means that it could be a universal game changer for any nearby planets. If a gamma ray burst were to occur near a planet, the radiation would likely be lethal to any life forms on that planet. For planets that are farther away, the radiation would still be powerful enough to cause serious damage, potentially altering the conditions for life or triggering a mass extinction. Even the most resilient life forms would struggle to survive such an intense event, and many would not be able to withstand the long-term effects of the radiation. The level of destruction caused by a hypernova's radiation is far beyond what we experience from most cosmic events. The power of the radiation, coupled with its ability to travel across vast distances, makes it one of the most dangerous forces in the universe. Planets in the immediate vicinity of the explosion would likely be completely wiped out, and even those farther away could face lasting effects from the intense gamma rays and X-rays. Whether a planet's atmosphere is destroyed or its ecosystems are irreversibly damaged, the chances of survival for life in the wake of a hypernova are slim. This is why hypernovae are such a potent force in the universe, shaping not just the stars around them, but also the planets in their path. Hypernovae come from stars that are much more massive than the stars responsible for supernovae. The larger the progenitor star, the more mass it has and the more energy it can produce. This increase in mass directly leads to an increase in the energy released during the star's final explosion. When a star of 30 times the mass of the Sunday or more reaches the end of its life and collapses, the result is a hypernova, a much more intense and destructive event than the death of a smaller star. The process that leads to a hypernova starts similarly to that of a supernova. In both cases, the star exhausts its nuclear fuel and gravity causes the core to collapse. For a typical supernova, this collapse might lead to the formation of a neutron star, or in some cases, a black hole. However, for a star that is significantly more massive, at least 30 times the mass of the Sunday, the collapse is much more violent, resulting in a hypernova. These stars burn through their fuel faster than smaller stars, and when they finally run out of fuel, the collapse that follows is far more extreme. One of the key differences between hypernovae and supernovae is the size of the progenitor star. Supernovae occur in stars that are between 8 and 20 times the mass of the Sunday, while hypernovae require a star with at least 30 times the mass of the Sunday. The larger mass means the star's core reaches much higher temperatures and pressures during its life. When it finally reaches the end of its life, the collapse of such a massive core produces far more energy. This energy is then released in the form of the intense explosion we observe as a hypernova. The greater mass of a hypernova progenitor leads to a much greater energy output. The star's greater size and the rapid collapse of its core allow for a more concentrated release of energy. While a supernova explosion can be incredibly bright, a hypernova is many times more energetic. The intensity of a hypernova can be so great that it briefly outshines an entire galaxy. This means that a hypernova's energy output is not just higher in volume, it's also released in a more concentrated form, making it far more destructive. The shock waves and radiation from a hypernova can reach farther and cause more damage to any nearby planets, gas clouds, and stars. In addition to the greater energy released, hypernovae also have more far-reaching effects on their surroundings. The explosion of a hypernova produces a much more powerful shock wave that can travel across vast distances, pushing gas and dust into new regions of space. This can lead to the formation of new stars as the compressed gas is forced to collapse under its own gravity. The energy from the hypernova is not just destructive, it also helps shape the future of the galaxy, triggering the birth of new stars and elements. The massive progenitor stars that give rise to hypernovae also differ in the way they burn their fuel. Smaller stars, like our Sun, burn hydrogen for most of their lives. Once they run out of hydrogen, they begin fusing heavier elements like helium, carbon, and oxygen. These smaller stars eventually shed their outer layers and become white dwarfs or neutron stars. In contrast, more massive stars burn through their fuel much faster, leading to the formation of heavier elements much earlier in their lives. The massive core of the star continues to collapse until the energy released is enough to trigger a hypernova, a more extreme version of the process. The energy produced by the massive progenitor stars of hypernovae is not just a result of their greater mass, but also of the rapid rate at which they burn through their fuel. The life of a star that will become a hypernova is much shorter than that of smaller stars. While stars like our Sun can live for billions of years, stars that eventually explode as hypernovae may only last a few million years. This is because the larger the star, the faster it consumes its fuel. As a result, a hypernova happens relatively quickly in cosmic terms, releasing a massive amount of energy in a short period of time. The core collapse in a hypernova is far more extreme than in a supernova. While both involve the star's core collapsing under its own gravity, the collapse of a more massive star generates much higher temperatures and pressures. This leads to a more violent explosion. The collapse is not only more powerful, but the material expelled in the explosion is also more energetic. The energy released by a hypernova can trigger a gamma ray burst, an intense burst of radiation that can last from a few seconds to several minutes. This burst is much more concentrated than anything produced by a supernova, and the energy released in these bursts can be detected from billions of light years away. In a typical supernova, the explosion of the star releases a large amount of energy, but the resulting explosion is often spread out over a larger area. In contrast, the hypernova's explosion is much more focused, and the energy is released in a much smaller volume, making it more intense. This is why hypernovae are capable of generating gamma ray bursts. These bursts are the result of the highly concentrated energy released in the collapse of the more massive star. While the increased mass of the progenitor star leads to a more powerful explosion, it also has a direct impact on the type of remnants left behind. In a supernova, the remnant might be a neutron star, which is a dense object formed from the collapse of the core. In the case of a hypernova, the collapse often leads to the formation of a black hole. This is because the mass of the collapsing core is so great that even neutron degeneracy pressure, which can prevent further collapse in smaller stars, is no longer enough to halt the process. Instead, the core collapses all the way to a singularity, creating a black hole. The energy released during this process is what drives the hypernova and results in the creation of the powerful gamma ray bursts associated with these events. The greater mass of the progenitor star also means that hypernovae leave behind more substantial remnants. In the aftermath of a supernova, the outer layers of the star are expelled, leaving behind a nebula made up of gas and dust. These remnants can go on to form new stars and planetary systems. In a hypernova, the energy released is so great that it not only creates a larger nebula, but also creates conditions for the formation of more massive objects. The shock waves from the explosion can compress surrounding gas clouds, triggering new rounds of star formation. In conclusion, hypernovae are far more destructive than supernovae due to the immense size and energy of their progenitor stars. The larger the star, the more mass it has, and the greater the energy it releases when it explodes. Hypernovae not only release more energy, but also have a more focused and concentrated impact, making them much more destructive and far-reaching than supernovae. The massive progenitor stars that create hypernovae live much shorter lives, burning through their fuel rapidly and ending in a far more violent explosion. These explosions leave behind powerful remnants and can trigger the formation of new stars, reshaping the surrounding space. A hypernova is a much more intense and longer-lasting explosion than a typical supernova. While a supernova generally lasts for a few weeks to a few months, the explosion of a hypernova can persist for several days to weeks, with its effects stretching out over a much longer period. The difference in duration between the two is a result of the vastly greater energy and mass involved in the hypernova, as well as the larger and more powerful processes that occur during its explosion. In a typical supernova, the star goes through a rapid collapse of its core, followed by an explosion that ejects the outer layers of the star into space. This release of energy creates a bright burst of light which can outshine an entire galaxy for a short time. The energy from the explosion gradually fades as the outer layers of the star disperse, and the shock wave travels outward. The entire event may last anywhere from a few weeks to a few months. While this is an immense amount of time in human terms, it is a relatively brief event in the life cycle of a star. In contrast, the explosion of a hypernova is far more energetic and complex. When a massive star, usually more than 30 times the mass of our Sunday, reaches the end of its life, its core collapses with incredible force. This collapse triggers a much more violent explosion, known as a hypernova. Unlike the quick release of energy seen in a supernova, a hypernova's explosion lasts much longer. The primary reason for this extended duration is the immense energy generated during the collapse of such a massive star. The more massive the star, the longer it takes for the core to collapse completely, and the more energy it releases as a result. The explosion of a hypernova involves the creation of a black hole or a neutron star at the center of the collapsing star. The outer layers are blasted away, but the energy release doesn't dissipate as quickly as in a supernova. Instead, the shock waves and the radiation continue to travel outward, creating a prolonged period of intense activity. For several days to weeks, the energy released can continue to shine brightly, making the hypernova far more visible over a longer period of time compared to a supernova. This prolonged duration also means that the after effects of a hypernova linger much longer. The shock waves from the explosion take time to spread out into space, interacting with the surrounding gas and dust. These shock waves compress nearby material, which can trigger the formation of new stars. The energy released from the hypernova can also continue to be released as radiation over time, with gamma, ray bursts and X-rays traveling across vast distances. As the material from the explosion disperses, it continues to glow and interact with other matter, creating an expanding nebula that can persist for millions of years. An example of this extended duration can be observed in certain hypernova remnants. After the initial explosion, the remnants of the star continue to emit energy, and the shock waves interact with the surrounding space, causing the gas and dust to heat up and glow. These nebulae can remain visible for extended periods, with the energy from the explosion still detectable long after the event has passed. The remnants of a hypernova, often in the form of a pulsar wind nebula or a supernova remnant, can continue to be observed for thousands or even millions of years, making them a lasting mark of the violent death of a massive star. The extended duration of a hypernova explosion also plays a role in how the surrounding space is affected. For instance, the energy released by the explosion can continue to affect nearby stars and gas clouds, pushing them into new formations and triggering the creation of new stars. The longer the hypernova's effects last, the more time there is for these changes to take place. The shock waves from a hypernova can trigger a chain reaction, compressing gas clouds and leading to the birth of new stars. This prolonged influence can reshape entire regions of space, with the material from the explosion mixing with the interstellar medium and contributing to the creation of new celestial bodies. Hypernovae also differ from supernovae in their ability to produce long-lasting gamma-ray bursts. Gamma-ray bursts are one of the most powerful forms of radiation in the universe and are often associated with hypernovae. These bursts are so intense that they can last from a few seconds to several minutes, with the energy being emitted in tightly focused beams. The gamma-ray burst from a hypernova can continue for several days, making it far more prolonged than the burst of radiation from a supernova. The energy released in these bursts is enough to be detected across billions of light years, and their effects can have a lasting impact on the surrounding space. In comparison, the gamma-ray burst from a supernova, while still powerful, is not as intense or as prolonged. Supernovae generally produce shorter bursts of radiation that last for only a few seconds or minutes. The explosion itself is still incredibly energetic, but the duration of the burst is much shorter compared to that of a hypernova. This difference in duration is one of the reasons hypernovae are often considered more destructive than supernovae. In the case of a hypernova, the energy released is so intense that it can continue to impact the surrounding space long after the initial explosion. The radiation and shock waves can trigger changes in the interstellar medium, cause the formation of new stars, and influence the behavior of nearby galaxies. This extended duration gives hypernovae a far-reaching impact on their surroundings, influencing the space around them for millions of years. While supernovae are extremely bright and powerful, their effects tend to be more short-lived compared to hypernovae. The explosion of a supernova may outshine an entire galaxy for a few weeks or months, but the energy it releases quickly fades as the shock waves and radiation spread out into space. Hypernovae, on the other hand, continue to release energy for a much longer time, with the explosion lasting several days to weeks. This longer duration makes the effects of a hypernova far more far-reaching and influential, as the energy continues to shape the surrounding space and the remnants of the explosion remain visible for a much longer period. Ultimately, the duration of a hypernova explosion is one of the key factors that sets it apart from a supernova. The larger mass of the progenitor star and the more intense collapse lead to a longer-lasting release of energy, which has a profound effect on the surrounding space. Whether through the creation of new stars, the emission of radiation, or the lasting influence of the shock waves, the duration of a hypernova explosion makes it one of the most dramatic and far-reaching events in the universe. When a hypernova occurs, one of the most dramatic features of the explosion is the launch of ultra-fast jets of material, often traveling at nearly the speed of light. These jets, which are directed along the poles of the collapsing star, carry massive amounts of energy and can have a profound impact on the surrounding space. These high-speed jets not only send matter across vast distances, but also emit deadly radiation, including gamma rays and X-rays, making them a significant force in the cosmos. The energy and radiation they produce can disrupt the fabric of space-time itself, creating ripples that affect everything in their path. These jets are the result of the extreme conditions generated during the collapse of a massive star. When a star that is at least 30 times the mass of our Sun reaches the end of its life, its core collapses inward. This collapse creates a black hole or neutron star at the center of the explosion. As the material falls inward, powerful magnetic fields are generated, which help channel the ejected material into narrow, fast-moving jets. These jets shoot outward from the poles of the newly formed black hole, carrying immense amounts of energy along with them. The speed of these jets is almost incomprehensible. Moving at close to the speed of light, the jets can travel across vast distances in a fraction of the time it would take for normal matter to move. This means that a hypernova's jets can reach parts of the universe far from the original explosion. The material in these jets consists mostly of high-energy particles, including protons and electrons, which move so quickly that they can travel through space without being significantly affected by the normal forces that slow down particles in a less extreme environment. One of the most striking aspects of these jets is the radiation they emit. As the particles in the jets move at such high speeds, they release huge amounts of energy in the form of radiation. This radiation includes X-rays and gamma rays, which are some of the most dangerous forms of light in the universe. The intensity of the radiation is so high that it could have serious effects on any nearby stars, planets, or even entire galaxies. If a hypernova were to occur close to a planet, the radiation could strip away its atmosphere, making it uninhabitable and potentially sterilize any life forms that may be present. For planets farther away, the radiation might still affect them, though the intensity would be lessened over time and distance. The energy and radiation released by the jets are not just dangerous to nearby objects, they also carry immense power across vast stretches of space. These high-speed jets can interact with the surrounding gas and dust, compressing it and triggering new star formation. In some cases, the jets may even be powerful enough to disrupt the formation of new stars or galaxies, altering the course of cosmic evolution. The jet's ability to affect the surrounding medium is an important part of their cosmic impact. The power of these jets can also affect space, time itself. The collapse of a massive star into a black hole, combined with the release of energy in the form of jets, can cause ripples in the fabric of space. These ripples, known as gravitational waves, are disturbances that spread outward from the source. Much like the ripples created by a stone dropped into a pond, gravitational waves travel through space at the speed of light, carrying information about the event that created them. In the case of a hypernova, the release of energy and the formation of a black hole are so intense that they generate powerful gravitational waves, which can be detected even billions of light years away. The cosmic impact of these jets extends beyond just the material they move or the radiation they emit. As they travel through space, they have the potential to alter the structure of the universe itself. The jets can cause gas and dust clouds to compress, leading to the formation of new stars. They can also push nearby objects out of their orbits, causing them to collide or scatter. The energy carried by the jets can even cause changes in the motion of entire galaxies. By interacting with the interstellar medium, these jets become a powerful force that shapes the larger structure of the universe. In addition to these immediate effects, the energy and radiation from the jets can travel through space for billions of years, continuing to influence the areas they pass through. This means that even if the original hypernova has long since passed, the jet's effects could still be felt in distant parts of the universe. The energy released by the jets can continue to affect nearby stars, gas clouds, and even distant galaxies, altering their paths or triggering new star formation. One famous example of the impact of hypernova jets is the gamma ray burst, GRB 080916c. This burst, which originated from a hypernova event in a distant galaxy, was one of the most powerful gamma ray bursts ever observed. The jet from this explosion was so intense that it sent out radiation that could be detected across billions of light years. The energy from the burst interacted with the surrounding space, affecting the gas and dust around it, and causing ripples in space, time that could be observed by astronomers. GRB 080916c is a prime example of how the energy and radiation from hypernova jets can travel across vast distances and impact everything in their path. The jets produced by a hypernova are not only a source of intense radiation, but also a driver of change in the universe. Their ability to compress gas, trigger star formation, and influence the motion of galaxies makes them a powerful force in shaping the cosmos. These jets are a reminder of the immense power that exists in the universe and the dramatic events that occur when massive stars reach the end of their lives. The lasting effects of hypernova jets are still being studied by astronomers, as scientists continue to explore how these powerful bursts of energy affect the surrounding space. The more we learn about these jets, the better we can understand the larger forces at play in the universe. While the immediate impact of the jets is destructive, their ability to shape the environment and trigger the formation of new stars also plays a vital role in the ongoing evolution of the cosmos. In the end, the cosmic impact of hypernova jets is both destructive and creative. The energy they release has the power to disrupt space, time-destroy planets, and alter the course of galaxies. But it also drives the birth of new stars and elements. These jets are an essential part of the life cycle of massive stars, marking the end of one chapter in the universe's history and contributing to the beginning of another. Hypernovae are far rarer than supernovae. Supernovae happen more frequently in the universe, with one occurring roughly once every 50 years in a typical galaxy. In contrast, hypernovae are exceedingly rare events. They occur only once every several hundred to several thousand years in a typical galaxy. This vast difference in frequency is due to the specific conditions required for a hypernova to take place. Supernovae arise from the death of massive stars, typically those with a mass between 8 and 20 times that of the Sun. These stars are relatively common in the universe. When they run out of fuel, they collapse under their own gravity, triggering a massive explosion. This is a well-understood and relatively frequent event in the life cycle of stars. The larger the star, the more likely it is to eventually die in a supernova. Because these stars are common and relatively short, lived supernovae occur regularly across galaxies. Hypernovae, however, are much rarer because they require a much more massive progenitor star, typically one that is more than 30 times the mass of our Sun. Stars of this size are far less common than their smaller counterparts. In fact, stars of such enormous mass are relatively few in number, and their lives are even shorter. They burn through their fuel at a rapid rate and tend to have very brief lifetimes in cosmic terms. This means that hypernovae are the end result of a rare and short-lived group of stars, making them much less frequent than supernovae. The rarity of hypernovae can be better understood when considering the birth rates of massive stars. Stars are born from clouds of gas and dust, and the process of star formation depends on the amount of material available and the conditions in the surrounding environment. While the universe has plenty of gas and dust, the formation of stars that are large enough to become hypernovae is a more selective process. These stars are born in regions where there is a high concentration of gas, but even in these areas, only a small fraction of the stars will reach the enormous sizes required for hypernovae. Once these massive stars are formed, they follow a different path compared to less massive stars. A typical star like the Sun will live for billions of years, slowly burning through its hydrogen and eventually swelling into a red giant before shedding its outer layers. In contrast, the most massive stars live much shorter lives. These stars burn through their fuel rapidly, and when their hydrogen runs out, they move quickly through later stages of fusion, eventually collapsing into a black hole or neutron star. The process is fast and intense, but it only happens for a small fraction of stars. Because the stars that lead to hypernovae are rare, the explosions themselves are even rarer. The likelihood of one of these stars reaching the end of its life and producing a hypernova is low, especially when compared to the much more common supernova. As a result, while supernovae are observed regularly in distant galaxies, hypernovae are not something we expect to see frequently. In fact, astronomers may go many years without observing a hypernova, even though supernovae are more common and more easily detected. Hypernovae also differ from supernovae in the way they are detected. While supernovae are visible to the naked eye and can be observed in distant galaxies, hypernovae are much harder to detect due to their rarity and the fact that their jets are focused in specific directions. The immense energy from a hypernova is emitted in narrow beams, and if the explosion is not directed toward Earth, we may not detect it at all. Additionally, hypernovae can sometimes be confused with other cosmic events, such as gamma ray bursts, which are also associated with the death of massive stars. This makes it even harder to directly observe and count hypernovae, further contributing to their rarity. In a typical galaxy, the occurrence of a hypernova is so infrequent that astronomers may only witness one or two in their lifetime. For example, if a galaxy experiences a hypernova only once every 1,000 years, and the average human lifetime is about 80 years, the chances of observing a hypernova in any given human lifetime are extremely low. Even in the most well-studied galaxies, the rare nature of hypernovae means they are not something we see regularly. The rarefied nature of these explosions makes them even more fascinating when they do occur, as they are the result of some of the most extreme and energetic processes in the universe. Despite their rarity, hypernovae are incredibly important to our understanding of the cosmos. They are responsible for creating some of the heaviest elements in the universe, such as gold and uranium. These elements are scattered across space, enriching the interstellar medium and later becoming part of new stars, planets, and even life. The energy released by a hypernova also plays a role in shaping the structure of galaxies, as the shock waves from these explosions can trigger new star formation by compressing nearby gas clouds. Hypernovae are thus a key piece of the cosmic puzzle, even though they occur much less frequently than supernovae. The rarity of hypernovae is also tied to the frequency of large stars. Stars that are large enough to undergo a hypernova are relatively few, and they are typically located in regions with a higher concentration of gas and dust. These regions, known as star-forming nebulae, are where most new stars are born. While these nebulae are abundant in the universe, only a small fraction of the stars born there will become massive enough to explode as a hypernova. The combination of fewer massive stars and their short lifetimes contributes to the overall rarity of these events. Hypernovae are also affected by the age of the universe. As the universe continues to evolve, fewer massive stars are being formed. In the early universe, there was a greater abundance of gas, leading to more massive stars being born and eventually dying in supernovae or hypernovae. As the universe ages and star formation slows down, the rate of hypernovae will continue to decline. This means that while hypernovae may have been more common in the early universe, they are becoming rarer as time goes on. Despite their infrequency, hypernovae are a reminder of the extreme forces at play in the universe. They show us the death of massive stars and the immense energy released during these final moments. Although they are much rarer than supernovae, hypernovae are an important aspect of stellar evolution, and contribute to the creation of the heavy elements that shape the universe around us. Their rarity makes them even more valuable to scientists, as each one provides a unique insight into the workings of the cosmos. In binary star systems, two stars orbit each other, sometimes close enough that their gravitational interactions can have significant effects on their evolution. If one of these stars reaches the end of its life and explodes as a supernova, the shock wave and expelled material will affect the entire system. In most cases, this causes a dramatic disruption, but when the explosion is a hypernova, an even more extreme version of a supernova, the consequences are far greater. Hypernovae in binary systems can eject massive amounts of material at incredibly high speeds, potentially altering the entire structure of the system and dramatically changing the orbits of the remaining stars. A typical supernova in a binary system occurs when one of the stars, having reached the end of its life, collapses under its own gravity. The collapse triggers a violent explosion, blowing off the outer layers of the star and releasing a tremendous amount of energy. In many cases, this can disrupt the orbit of the second star in the binary system. If the explosion is powerful enough, it might even eject the surviving star from the system altogether, sending it off into space. While this event is violent and disruptive, the overall structure of the system may not be completely altered, especially if the stars were not in close orbit. However, the impact of a hypernova on a binary system can be much more catastrophic. A hypernova happens when a star with a mass of at least 30 times that of the Sun undergoes a collapse. The resulting explosion releases far more energy than a regular supernova and ejects material at speeds close to the speed of light. This amount of force can send shockwaves through the entire star system, and the expelled material can travel much farther than what is ejected in a typical supernova. The material released in a hypernova is much more massive and energetic, which can completely alter the gravitational dynamics of the binary system. In a binary system, both stars are bound together by their mutual gravity. However, if one of the stars undergoes a hypernova, the ejected material can push the other star away. The force of the explosion may be enough to change the orbit of the surviving star. If the stars are in close orbit, the hypernova could eject the second star entirely from the system, sending it flying through space at high velocity. The energy released by the hypernova could also cause the stars to move in such a way that they no longer remain in a stable orbit, leading to a complete disruption of the system's structure. A hypernova in a binary system can also create a situation where the remaining star is pushed toward the black hole, or neutron star, formed from the collapsed core of the original star. If the surviving star gets too close to the newly formed black hole, it may be pulled into it, leading to its eventual destruction. This would leave the black hole alone, having consumed the entire binary system. Even if the surviving star manages to escape the system, the damage done by the hypernova's shockwave would still have lasting effects on its orbit and the surrounding space. In some cases, a hypernova might even trigger the formation of new objects in the system. The massive shockwaves and radiation emitted by the explosion can compress surrounding gas and dust clouds, potentially sparking new star formation. If this material is dense enough and is compressed by the energy of the explosion, it could collapse under its own gravity to form a new star or planet. However, the destruction caused by the hypernova is so extreme that the chances of forming stable systems afterward are low. The newly formed stars would likely face an environment of high radiation and unstable conditions, making it difficult for life to form or thrive in the aftermath of such an event. The massive amount of energy released in a hypernova could also lead to the creation of relativistic jets, narrow beams of energy that travel at nearly the speed of light. These jets can shoot material far out into space, affecting anything in their path. If the binary system is close enough to the path of one of these jets, it could strip away the remaining material from the surviving star or disrupt its orbit entirely. The intensity of these jets could also cause further heating of any nearby gas clouds, further complicating the evolution of the system. While the effects of a hypernova in a binary system are dramatic, they are also incredibly rare. The stars in these systems must be massive enough to undergo a hypernova, and binary systems with stars of this size are less common than those with smaller stars. Hypernovae themselves are already much rarer than typical supernovae, making them an unusual event in the universe. However, when they do occur, the consequences for the system are far-reaching. One example of the potential impact of such an event can be seen in the binary star system called SS433. While not the result of a hypernova, SS433 is an example of how the interaction between two stars in a binary system can lead to dramatic changes in the system. One of the stars in SS433 is a massive blue giant that feeds material to its companion, a compact object, likely a neutron star or black hole. The interaction between these stars creates powerful jets of material, similar to the jets created in hypernovae. These jets are so strong that they affect the surrounding space, and their energy has been studied by astronomers as a way to understand the role of high-energy explosions in binary systems. If SS433 were to experience a hypernova, the result would likely be a much more violent disruption of the system, with a high likelihood that the stars would be ejected from the system or pulled into a black hole. The interaction of stars in binary systems is one of the most fascinating areas of study in astrophysics. When one star explodes as a supernova or hypernova, it not only marks the end of the star's life, but also triggers a series of events that can dramatically alter the surrounding system. In the case of a hypernova, the impact on the surviving star can be far more intense, potentially leading to the destruction of the entire system or the formation of new objects from the expelled material. These explosions remind us of the power and complexity of stellar evolution, and the ways in which even the death of a star can shape the future of its environment. In binary star systems, two stars orbit each other, sometimes close enough that their gravitational interactions can have significant effects on their evolution. If one of these stars reaches the end of its life and explodes as a supernova, the shockwave and expelled material will affect the entire system. In most cases, this causes a dramatic disruption. But when the explosion is a hypernova, an even more extreme version of a supernova, the consequences are far greater. Hypernovae in binary systems can eject massive amounts of material at incredibly high speeds, potentially altering the entire structure of the system and dramatically changing the orbits of the remaining stars. A typical supernova in a binary system occurs when one of the stars, having reached the end of its life, collapses under its own gravity. The collapse triggers a violent explosion, blowing off the outer layers of the star and releasing a tremendous amount of energy. In many cases, this can disrupt the orbit of the second star in the binary system. If the explosion is powerful enough, it might even eject the surviving star from the system altogether, sending it off into space. While this event is violent and disruptive, the overall structure of the system may not be completely altered, especially if the stars were not in close orbit. However, the impact of a hypernova on a binary system can be much more catastrophic. A hypernova happens when a star with a mass of at least 30 times that of the Sun undergoes a collapse. The resulting explosion releases far more energy than a regular supernova and ejects material at speeds close to the speed of light. This amount of force can send shockwaves through the entire star system, and the expelled material can travel much farther than what is ejected in a typical supernova. The material released in a hypernova is much more massive and energetic, which can completely alter the gravitational dynamics of the binary system. In a binary system, both stars are bound together by their mutual gravity. However, if one of the stars undergoes a hypernova, the ejected material can push the other star away. the force of the explosion may be enough to change the orbit of the surviving star, making it unstable. If the stars are in close orbit, the hypernova could eject the second star entirely from the system, sending it flying through space at high velocity. The energy released by the hypernova could also cause the stars to move in such a way that they no longer remain in a stable orbit, leading to a complete disruption of the system's structure. A hypernova in a binary system can also create a situation where the remaining star is pushed toward the black hole or neutron star formed from the collapsed core of the original star. If the surviving star gets too close to the newly formed black hole, it may be pulled into it, leading to its eventual destruction. This would leave the black hole alone, having consumed the entire binary system. Even if the surviving star manages to escape the system, the damage done by the hypernova's shockwave would still have lasting effects on its orbit and the surrounding space. In some cases, a hypernova might even trigger the formation of new objects in the system. The massive shockwaves and radiation emitted by the explosion can compress surrounding gas and dust clouds, potentially sparking new star formation. If this material is dense enough and is compressed by the energy of the explosion, it could collapse under its own gravity to form a new star or planet. However, the destruction caused by the hypernova is so extreme that the chances of forming stable systems afterward are low. The newly formed stars would likely face an environment of high radiation and unstable conditions, making it difficult for life to form or thrive in the aftermath of such an event. The massive amount of energy released in a hypernova could also lead to the creation of relativistic jets, narrow beams of energy that travel at nearly the speed of light. These jets can shoot material far out into space, affecting anything in their path. If the binary system is close enough to the path of one of these jets, it could strip away the remaining material from the surviving star or disrupt its orbit entirely. The intensity of these jets could also cause further heating of any nearby gas clouds, further complicating the evolution of the system. While the effects of a hypernova in a binary system are dramatic, they are also incredibly rare. The stars in these systems must be massive enough to undergo a hypernova, and binary systems with stars of this size are less common than those with smaller stars. Hypernovae themselves are already much rarer than typical supernovae, making them an unusual event in the universe. However, when they do occur, the consequences for the system are far-reaching. One example of the potential impact of such an event can be seen in the binary star system called SS433. While not the result of a hypernova, SS433 is an example of how the interaction between two stars in a binary system can lead to dramatic changes in the system. One of the stars in SS433 is a massive blue giant that feeds material to its companion, a compact object, likely a neutron star or black hole. The interaction between these stars creates powerful jets of material, similar to the jets created in hypernovae. These jets are so strong that they affect the surrounding space, and their energy has been studied by astronomers as a way to understand the role of high-energy explosions in binary systems. If SS433 were to experience a hypernova, the result would likely be a much more violent disruption of the system, with a high likelihood that the stars would be ejected from the system or pulled into a black hole. The interaction of stars in binary systems is one of the most fascinating areas of study in astrophysics. When one star explodes as a supernova or hypernova, it not only marks the end of the star's life, but also triggers a series of events that can dramatically alter the surrounding system. In the case of a hypernova, the impact on the surviving star can be far more intense, potentially leading to the destruction of the entire system or the formation of new objects from the expelled material. These explosions remind us of the power and complexity of stellar evolution, and the ways in which even the death of a star can shape the future of its environment. When a star reaches the end of its life and explodes, it releases an enormous amount of material into space. This material includes a range of elements, some of which are essential for the formation of new stars, planets, and even life. Both supernovae and hypernovae contribute to this process. But the key difference lies in the amount and variety of heavy elements that are expelled. While both types of explosions scatter elements like iron, oxygen, and carbon into space, hypernovae release far greater quantities of these elements, contributing more significantly to the creation of new solar systems in the future. A supernova occurs when a massive star, typically between 8 and 20 times the mass of our Sun, reaches the end of its life. When the star runs out of fuel, its core collapses, and the outer layers are violently ejected into space. The explosion creates a shockwave that travels through space, heating up and compressing surrounding gas and dust. This process generates heavy elements like iron, nickel, and cobalt, which are created in the intense heat and pressure of the explosion. These elements are then scattered into the interstellar medium, enriching the space around the star and setting the stage for the formation of new stars, planets, and even life. Hypernovae, on the other hand, are far more powerful and occur in stars that are at least 30 times the mass of the Sun. These stars burn through their fuel much faster than smaller stars. And when they collapse, the resulting explosion is far more energetic. In addition to the shockwave and the ejection of material, hypernovae also release much larger amounts of heavy elements into space. The sheer energy of the explosion allows for the creation of even heavier elements, such as gold, uranium, and platinum. These elements are vital for the formation of rocky planets like Earth, and are key to the existence of life as we know it. The reason hypernovae release larger quantities of heavy elements is due to the extreme conditions generated by the collapse of such a massive star. As the star's core collapses, temperatures and pressures rise to levels much higher than those seen in a typical supernova. This allows for the creation of a broader range of elements, including those heavier than iron, which cannot be formed in the core of normal stars. The energy released in a hypernova explosion is sufficient to produce these elements, which are then blasted out into space and spread across vast distances. The material ejected by a hypernova can travel far beyond the original location of the star, enriching the interstellar medium and potentially providing the building blocks for future solar systems. Over time, this material mixes with gas and dust in the galaxy, and under the right conditions, it can condense and form new stars and planets. The elements created in hypernovae play a crucial role in this process. Without the heavy elements created by these explosions, the formation of rocky planets, like Earth, would be impossible. Life as we know it would not exist without the presence of elements like carbon, nitrogen, and oxygen, which are produced in these stellar explosions. In the distant future, the remnants of a hypernova could be part of a new star-forming region. As gas and dust clouds are compressed by the shock waves from the explosion, they can collapse under their own gravity, eventually forming new stars and planetary systems. The heavy elements released by the hypernova contribute to the composition of these new systems, making them more likely to support life. The process of star and planet formation is complex, but the heavy elements scattered by hypernovae provide the raw materials needed for the next generation of solar systems. Hypernovae also influence the environments of existing stars and planets. The energy released by the explosion can trigger the formation of new stars by compressing gas clouds in nearby regions. This is a form of feedback where the explosion of one star leads to the birth of others. Over millions of years, these new stars may form their own planetary systems, some of which could potentially support life. The heavy elements that are scattered by the hypernova provide the necessary ingredients for planets to form and develop the conditions needed for life. To put this into perspective, consider the case of our own solar system. The elements that make up Earth, including carbon, nitrogen, and oxygen, were created in previous generations of stars. When those stars exploded as supernovae or hypernovae, the heavy elements they produced were scattered into space, enriching the gas and dust clouds from which our Sunday and planets formed. If a hypernova were to occur near the formation of a new solar system, it would contribute even more heavy elements to the mix, making the process of planet formation more likely to produce rocky, life-supporting planets. The influence of hypernovae extends far beyond the immediate aftermath of the explosion. As the heavy elements they release spread throughout the galaxy, they contribute to the ongoing evolution of the universe. New generations of stars, planets, and galaxies are built from the material expelled by previous stellar explosions. The cycle of stellar birth and death is a key part of the cosmic process, and hypernovae play an important role in this cycle by providing the necessary elements for the creation of new worlds. While supernovae are more common, the heavier elements produced by hypernovae are crucial for the formation of planets capable of supporting life. Hypernovae create a wider range of elements and in larger quantities than regular supernovae. This means that the material they release has a greater potential to influence the formation of future solar systems. These events help explain the presence of heavy elements in the universe and how they are distributed across galaxies. In galaxies that are rich in massive stars, hypernovae could occur more frequently, enriching the surrounding space with a greater abundance of heavy elements. This would make it more likely that new star systems forming in these regions would have the raw materials needed for life. Conversely, in regions with fewer massive stars, the formation of these elements would be less frequent, making it harder for new, life-supporting systems to develop. Over time, as galaxies continue to evolve, and massive stars continue to explode, the heavy elements produced by supernovae and hypernovae will continue to shape the makeup of future solar systems. These elements play a central role in the development of rocky planets, the building blocks of life, and the ongoing creation of stars and galaxies. Hypernovae, with their immense energy and massive ejection of heavy elements, are crucial in this grand process. While they are rare, their impact on the formation of new solar systems is profound, and their contribution to the creation of the materials necessary for life cannot be overstated. When a hypernova occurs, it unleashes an enormous amount of radiation, and any life forms located within a few hundred light years of the explosion would face a high risk of extinction. The intense radiation, including deadly gamma rays and X-rays, would flood the surrounding space and have a catastrophic effect on any planets within that range. These forms of radiation are powerful enough to strip away a planet's atmosphere and harm life in ways that would make survival nearly impossible. The radiation from a hypernova can reach far across space, and its effects would be felt on planets that are located far from the original explosion. The radiation would be especially harmful to any planet within a few hundred light years, as the energy released in the explosion is so concentrated. Even if a planet is located at a distance where the shockwave itself doesn't reach, the radiation alone would still be potent enough to sterilize the planet. Without an atmosphere to shield it, the surface of the planet would be bombarded with harmful rays, disrupting any form of life. The radiation could cause severe damage to DNA, leading to mutations, cell death, and ultimately, the collapse of ecosystems. In contrast, a supernova, while still highly destructive, presents a somewhat different set of risks. A supernova results from the death of a star, but the energy released, though still immense, is not as concentrated as in a hypernova. The shockwave from a supernova can still strip away the atmosphere of nearby planets and increase radiation levels. However, if the planet is far enough away from the explosion, the effects could be less severe. In fact, life might survive if it is positioned at a sufficient distance, as the shockwave and radiation would lose their strength as they travel through space. For instance, the effects of a supernova on Earth would depend on its distance from the explosion. If the supernova were several thousand light years away, the shockwave and radiation would likely have less of an impact on our planet. The atmosphere might be slightly affected, and there could be an increase in cosmic radiation, but it would not be enough to completely wipe out life. However, if Earth were much closer to the supernova, the results would be far more catastrophic. The radiation could destroy the ozone layer, leaving the planet exposed to harmful ultraviolet rays from the sun. This would lead to an increase in cancer rates and other health problems for any life forms on the planet. The distance between a planet and the explosion is key in determining the likelihood of survival. For example, if a supernova were to occur just 20 light years away, the resulting radiation could be strong enough to cause significant damage to Earth's atmosphere. But if it were 200 light years away, the radiation would be much less intense by the time it reached Earth. In this case, life might still survive, though there would likely be long-term effects on the environment. On the other hand, the sheer power of a hypernova makes survival near it extremely unlikely, even at distances greater than those typically considered dangerous for supernovae. The radiation from a hypernova is far more intense and travels with much more energy, so even planets thousands of light years away could be affected. The deadly gamma rays and X-rays released in the explosion would have the capacity to destroy a planet's atmosphere, causing the surface to be exposed to the harsh conditions of space. Without an atmosphere, temperatures would fluctuate drastically, and the planet would become uninhabitable. One way to think about the difference in the effects of supernovae and hypernovae is to compare them to an explosion of different magnitudes. Imagine a firecracker versus a massive bomb. The firecracker might cause some damage if you are too close, but the damage becomes less severe as you move away from it. A massive bomb, on the other hand, could level an entire city even if you are miles away. Hypernovae are like that bomb, producing so much energy that their effects are felt at much greater distances, whereas supernovae are like the firecracker, still dangerous, but with a smaller radius of impact. In terms of biological survival, proximity to a hypernova would pose an almost certain risk of extinction for any life forms within a few hundred light years, even if life managed to survive the initial radiation burst. The longer-term effects would likely prove fatal. For example, the high levels of radiation could lead to a nuclear winter-like effect, where the atmosphere becomes filled with dust and debris from the explosion, blocking out sunlight and causing a dramatic drop in temperatures. This would make it difficult for plants to grow and disrupt the entire food chain. Supernovae, although still dangerous, would have less severe long-term effects at greater distances. Life on a planet located far enough from a supernova could survive, though ecosystems would likely be disrupted. For example, if Earth were located near a supernova, the radiation could damage the ozone layer, leading to more intense sunlight and the potential for more extreme weather. However, it would not be the death sentence that a nearby hypernova would present. One of the critical factors influencing survival is the speed at which radiation and shock waves travel through space. Gamma rays and X-rays travel at the speed of light. And as soon as a hypernova occurs, these waves can begin spreading out across the universe. The high-speed jets of material also released during a hypernova contribute to the distribution of this deadly radiation. Supernovae, while still releasing radiation, don't have the same kind of intense, focused energy that a hypernova generates. Thus, a supernova's effects are more diluted over space and time. While the effects of a supernova or hypernova on life are a serious concern, the likelihood of such an event occurring near our planet is extremely low. The nearest stars capable of producing a supernova or hypernova are far enough away that their radiation would not have a significant impact on Earth. However, if a hypernova were to occur within a few hundred light years, the survival of life on Earth would be at great risk. The radiation alone could wipe out life, and the long-term effects could alter the planet's environment for millions of years. Ultimately, the survival of life near a supernova or hypernova depends largely on the distance between the explosion and the planet. A supernova might not be lethal to life forms if it occurs far enough away, though it could still cause environmental changes that disrupt ecosystems. In contrast, the radiation from a hypernova would be far more intense and dangerous, leaving little chance for survival if it happens too close. While the odds of Earth being affected by such an event are low, the potential consequences underscore the immense power and danger of these cosmic explosions.